shit. Today we'll discuss on why numerical calculations are so important and how they're used in simulations and specifically video games. So strap in, grab your popcorns, and get ready for a journey to the inner workings of game engines. In the real world, every action and reaction is governed by the laws of physics. The universe calculates everything so we humans can focus on what we do best. Watch TikTok videos. Video games, however, being a simulation, don't have a universal law system. They simulate their version of reality based on a set of rules chosen by a designer. These rules usually resemble the real world, such as all objects are pulled downwards and objects cannot move through each other. But they're also bent to some extent because creating a game that is too realistic can get a little boring. The most important difference between video games and the real world is that video games do not exist continuously, but rather exist in separate frames, and every motion, action, and reaction seen there is nothing more than an illusion. When you look at this clip, you see a player moving forward. However, when we take a closer and slower look at it, we can see that this movement is not continuous, but rather compiled from many moments, also known as frames, shown one after the other. And while the game exists and is displayed only in these individual moments, the magic itself actually happens between them. Just a quick note before I start dissecting what happens inside the game engine. Today I'll be talking about the Unity game engine, which is what I'm familiar with and what I use in my physics-based platformer. I'll be releasing the first devlog in the coming weeks, so make sure to subscribe so you don't miss it. With that said, numerical calculations are at the heart of every world simulation, from industry flow, stress, heat, and acoustic simulations to video games. So the principles we'll discuss today will be relevant to all of these applications, with some slight variations in between them. In the Unity engine, movement is divided into two categories: kinematic movement and dynamic movement. Kinematic movement is where the velocity is set through code and physics is ignored. It is usually rigid and non-physical. The programmer decides what the velocity of an object will be in any case, and the engine moves the body accordingly. If the object is set to collide with another object, who gives a Physical interactions have no power here, and the object's velocity is set and must be respected. Some known examples are Hollow Knight's movement, where you immediately lose all momentum if you stop pressing the jump key, or as in many other games where your character starts moving at top speed the moment you press the move key. On the other hand, a dynamic movement is governed by collision detection and Newton's second law of motion, which help the engine calculate the object's velocity. The designer decides what are the forces that act on an object, for example movement force, gravity, etc., and the velocity is updated according to Newton's second law of motion. The best and most familiar example of this is gravity, that accelerates object downwards in a constant pace. Now that we've got a grip on what the types of movements are, let's show how they materialize in the game engine, starting with the simpler kinematic movement. As we mentioned, in this type of movement, the designer determines the object's velocity without the involvement of physics. Think of a projectile being shot and moving in a straight line rather than in a parabolic path. By definition, an object's velocity is the rate of change of its position. So, when the object is moving in a constant velocity, its path is a straight line, and the object's position along the line is determined by the following equation. Here, v is the velocity, t is the time at which we want to observe the object, and x0 is its initial position. A game engine, however, can't use this equation, and here's the most important part. It cannot use this equation because this equation assumes that the object is moving in a straight line the entire time. But the game engine just can't assume that. Why is that? Because many objects eventually change their velocity either through code if they're kinematic or through physics if they're dynamic, and the engine just cannot anticipate when that change might occur. If an object theoretically never changes the velocity, then yes, the engine can use that equation. Take a game like Flappy Bird, for example. If the player's horizontal velocity is constant the entire game, then this equation is okay to use. But as we know, it's usually not like this. Let's take an example. Assume we have a player starting here with this velocity. If we use this equation, we can see that this is its projected path. Every frame, the game engine can keep track of the time and calculate where the object is supposed to be, and everything works well. Now, assume that the player wants to change the velocity direction. So we change v in our equation. What we expect now is this path continuation. But using the same equation with a different velocity will yield this instead. That's because this equation is meant for a straight line motion only. In order to continue using this equation in a correct manner, we need to update the initial position of the object and reset the timer of t. Now things work again. What we essentially do is we set a new straight line path. But if the player wants to again make a change in the velocity, we need to do this equation update process again and so forth. So instead of checking every frame whether there's a change in the velocity, what engines basically do is update the equation every frame. Moreover, instead of resetting the timer of t every frame, engines use a constant time interval representing the time that passed between frames. This yields the following equation. This equation is the numerical counterpart of the original equation. It takes the player's current position, its velocity, and a known duration factor delta t, and calculates the object's position in the next frame according to this equation. This process happens every single frame. Delta t is called the time step, and it is defined as the time between the two frames. Another quick note, if it helps, you can picture every calculation as a frame, even though the physics is calculated on a different rate called physics update rate. It is crucial for games to differentiate between frame rate and physics update rates, so that people with different frame rates will experience the same physics. In this video, however, I'll use the layman term frame to help visualize the effect. Okay, but this is straight line motion. What about circular or parabolical movements? We know these exist in video games too, so how are these achieved? Well, this is where the magic happens actually. This equation can actually create any type of movement, and that's because every type of movement can be divided into small straight line movements. This is actually the basis of calculus, but we won't get into that in this video. Well, actually ever. Now you see why in the previous video I called this an aggregate calculation. That's because in each frame we build on the last frame and add its contribution to get the next frame. This process is called numerical integration, and I'll explain why later in the video. Dynamic bodies are like kinematic bodies, but with an extra layer of physics. While the kinematic body calculation depended on the velocity or the position being updated by some code or the press of a key, the dynamic case gets the velocity through physics calculations. To understand this process, let's first discuss the inputs. Here, the input is force. From that, the engine needs to somehow calculate the velocity, and from that, well, we already know how to get the position. Time for a bit of physics. According to Newton's second law of motion, an object with mass m that is acted upon by a total force F will experience an acceleration in the direction of that force and with magnitude according to this equation. Most people like to teach this formula looking like this. But while it looks better, I think it's losing the important part of cause and effect. Because a force acts on the object, and because its mass is m, then the acceleration is what it is, not the other way around. Anyway, back to our case. Knowing the object's mass and the forces that act on it, whether it's a force that the player creates by pressing some key, or a force like gravity that always acts, or other, the engine calculates the object's acceleration. And how does that help? Well, the acceleration is the rate of change of the velocity. So we can calculate the velocity using this equation. Looks familiar? That's the same equation we used earlier for the position calculation using velocity, only now we're calculating the velocity using the acceleration. And just like before, the game engine does not use this equation, but rather its numerical equivalent. And if we plug the expression for the acceleration, we get this one. The game engine uses this equation every frame to calculate the current velocity of the object, and from that determines the object's position in the next frame using the equation from earlier. Just as before with the velocity, here we use the approximation where the acceleration is constant in between frames. That's the approximation the game engine uses. While not perfectly correct, it is more than accurate enough for video games. Here's the entire process from start to finish. First, we get the force input. Then we calculate the acceleration. From the acceleration, we get the velocity. And from the velocity, we get the position. That's basically it. Now let's discuss why it is called numerical integration. The official name of this method is Euler integration, named after the man, the absolute legend, Leonhard Euler. If you're not familiar with this dude, you should definitely look him up. I'll just say here that his equations are used in fluid mechanics, solid mechanics, harmonic functions, and so much more. Hell, the man's even got a number named after him. Anyway, I digress. Let's say we get why it's called Euler. The man practically invented everything. But why integration? Well, remember how I said that the velocity is the position's rate of change, and the acceleration is the rate of change of the velocity? This was just another way of saying that the velocity is the time derivative of position, and acceleration is the time derivative of velocity. And what is a time derivative, you may ask? It is simply the amount a property changes over time. For example, velocity, which as we said is the position's rate of change, is defined as this. And in our terms, if delta t is the time between frames, then the velocity is simply the position difference over how long this change took. And in technical terms, is the time derivative of the position. Okay, but why am I telling you this? We're talking about integration, not derivation. Well, that's the point. The thing is that integration is defined as the opposite of derivation. So if derivation is what took us from x to v, that is, we use the time derivation on x to calculate v, then to get x from v, we need the opposite, integration. You can even see it clearer when we rearrange the equation like this. This looks almost exactly like the equation we used to calculate x earlier, but do you remember what delta x is? It is the difference in position. So we can write it like so, with x being the position in the next frame, and x0 being the current position. Plug that into the equation above, and we get what we started with. I can go further into how integrals are basically summations over many small time steps, and most people like to explain integrals using functions with trapezoidal.
And then the fourth trapezoid is going to look like that.
And show that the integral is basically the area underneath the curve.
So let's calculate the area of each of these, and then we will have our approximation for the area under the curve.
Anyway, you get the point. Integration can get super technical, and I just spared you hours of sitting through boring classes. You're welcome. Alright, that's the basic principle behind computer simulations in general and video games in particular. Thank you all for watching and for the continued support, that really means a lot. As usual, if you found this helpful, please like this video, add your comments, and share it with your friends. Subscribe and join our lab if you like this series. Thanks again for watching, and I'll see you in the next one. Cheers, guys!